Rudewright Academy. Learn it, teach it, remember it. Today we're talking about database sharding. It's what you do when one machine, even the biggest one money can buy, is not enough anymore. By the end, you'll know how to split a database across many machines, and how to choose the splitting rule, and how to rescue the whole thing when one key catches fire. Every system starts here. One application, writing to one database. And for a long while, that is genuinely fine because a single well-tuned machine is more powerful than people give it credit for. Watch the write traffic pour in. 10,000 writes a second and the box barely notices. So the product grows and we push harder. 20, 30, 50,000 writes a second. And somewhere around here, a good machine tops out. This is the ceiling. You can buy faster disks and more cores for a while, but there is a biggest machine you can buy. And past it, the database simply cannot keep up. Requests start piling up at the door faster than they drain. So here is the question this whole video answers. When the biggest box is still not enough, what do you do? Let me give you the picture that makes the fix obvious. Think of a library where one librarian personally holds every single book. She is drowning. And you do not fix that by hiring a stronger librarian. You build shelves. Split the books across 4 shelves. A through F on the first, G through M on the next, and so on down the aisle. Now a reader with a book in mind does not queue at one desk. They walk straight to the one shelf that holds their book. And 100 readers spread out across the whole aisle, each shelf carrying a slice of the load. But notice the new question the shelves quietly created. Which shelf? Every request now needs a rule that points it at exactly one place. Hold on to that question because it is the entire subject of this video. So here is the heart of sharding. In front of the shards, we put a router, a tiny piece of logic that every request passes through. A key goes in. The router applies one deterministic rule, and exactly one shard comes out. Same key, same answer, every single time. That rule has 2 ingredients. The shard key, which is the field we root on, and the function that turns it into a home. And here is the claim I want you to remember. Choosing that rule is the whole design. Get it right, and the load spreads across the fleet almost linearly. Get it wrong, and you will be rebuilding it live under production traffic months from now. There are 3 classic forms of this rule, and each one answers a different question. Rule number 1, range sharding. Each shard owns a contiguous slice of the key space. User EADs up to 1 million live on the first shard, 1 to 2 million on the second, and so on. Its superpower is the range scan. Ask for everything between 1.2 and 1.9 million, and that query touches exactly one shard which answers it sequentially right off one disk. That is why time-ordered stores love ranges. But now watch the curse. Suppose the key is a timestamp, so the slices become first quarter, second quarter, third, and fourth. Every new write carries today's date. So this write lands on the newest shard. The next one, the same shard. Every single one of them, the same shard. The newest shelf takes all the new books, while the rest of the aisle sits idle. So range sharding is the right answer when you truly scan ranges, and a trap when your keys arrive in order. Rule 2, hash sharding. Before routing, we feed the key through a hash function which scrambles it into what is effectively a dice roll. Fair, but deterministic. Watch 4 different keys arrive. The first one scatters here. The next lands somewhere else entirely. So does the next. And the next. Neighboring keys fly apart, the load spreads evenly, and no shelf is special. For point lookups, fetch this user, fetch that order, this is the default answer. But the price is exactly the thing we just loved. Ask for everything between 2 points now, and the answer is sprayed across every shard. One range query becomes a scatter and gather across the entire fleet. Even spread at the cost of your range scans. Remember that trade. Rule 3, the directory. Don't compute the answer at all. Look it up. A small lookup service holds an explicit map. This key lives on shard 1. That tenant lives on shard 3. Every request now takes 3 steps. First, to the router. Then a lookup in the directory. Then onto whichever shard the map names. And that map buys you total control. Move one row and that key now lives on different hardware. No rehashing and nobody else is disturbed. But look at the costs. Every single request pays that extra hop. And worse, if the directory goes down, every key in the system is unfindable. So the directory has to be cached and replicated like your life depends on it. Because at that moment, it does. So how do you actually choose? 3 rules, 3 questions. Question 1. Do you scan ordered ranges? If yes, take range sharding. 1 shard per scan and keep a plan for the hot end. Question 2. Are you doing point lookups and you want even load with no ceremony? Hash it. This is the default, and most systems should start here. Question 3. Do you need to move specific keys at will or treat some tenants specially? That is the directory. Total control for an extra hop. And notice that you can compose them. Hash for the crowd, a directory for the exceptions. Keep that composition in mind because the second half of this video is about the exceptions. Now, the failure that eats more engineering time than any other in sharded systems. We shard a social app's activity by user ID hashed. Textbook correct. And for months, the load is beautifully even. Every shard carries its fair share. Then one account goes viral. Watch what happens to the traffic. The writes do not spread anymore. They all chase that one key onto that one shard. In a real incident of exactly this shape, the hot shard was sustaining about 18,400 writes every second, while the other shards averaged 850. Add those up across our 4 shards, and that is one box carrying 88% of everything, pinned red with a queue growing at its door, while its neighbors sit nearly idle. And here is the thing. The hash did nothing wrong. It spread the keys perfectly evenly. But traffic is not attached to keys evenly. And a hash gives each key exactly one home. So all of that heat lands on one box. Before I show you the fix, test yourself, because interviewers love this one. Would doubling the shard count fix it? Think about what the routing rule does with that one hot key. Take a second. Okay, here is the answer. We rehash across 8 shards instead of 4, and the hotkey still maps to exactly one of them. The other shards just gained more idle company. Adding shards spreads keys. It does not split the heat inside a single key. To fix this, we have to change the rule for that one key. And that is a ladder with 4 rungs, cheapest first. Rung 1, salting. We split the hotkey into several subkeys by appending a tiny random suffix. 0, 1, 2, or 3. Now watch the same fire hose of writes. The first salted write hashes here. The next one lands on a different shard. The third, somewhere else again. And the fourth, on yet another. 4 salts, 4 different homes. The hot shard's load drops from 18,400 to about 4,600 per shard, right back inside a healthy envelope. But the bill arrives on the read side. To read the whole key, you must now ask all 4 salts and merge the answers. A fan out where a single lookup used to be. So salting is the right hotkey move. Take it when writes are the fire and reads can afford the fan out. Rung 2, local aggregation. It exists because most write hotkeys in the wild are counters. Likes, views, metrics. If the writes are increments, don't send every single one to the shard. Put a small combiner in front of it. Watch a burst of 12 increments arrive. The combiner absorbs every one of them. and then it flushes just a handful of combined writes through to the shard. 12 came in, 3 went out. And in production, the ratio is far more dramatic. 1,000 plus ones become one single plus 1,000. The shard sees a trickle, and the totals stay truthful. The only price is a few seconds of staleness on the counter. And for a like count nobody will ever notice. Rung 3, the dedicated shard. For the keys that no arithmetic can hide. Some tenants are simply whales. A mega account, a flagship customer. So stop pretending they're average. The router keeps a tiny hot list. And next to the fleet, we reserve a shard just for the whale. Watch the routing now. The whale's key checks the list first and routes straight to its own reserved hardware. An ordinary key misses the list and takes the normal hash path exactly as before. The whale gets a box sized for its heat and the fleet levels right out. And notice what we just built. It is the composition from earlier. Hash for the crowd, a directory for the exceptions. That is the standard production shape. Rung 4 is for a different kind of heat entirely. Everything so far was write heat. But when 10 million people all load one profile, that is red heat. And read heat has a cheaper answer. Copies. Here is our hot shard, drowning in 20,000 reads a second. We put a cache in front of it and grow read replicas behind it. Now watch a read arrive. It stops at the cache. It never touches the database at all. Another read, same story. When 99% of reads hit the cache, the shard's read load collapses from 20,000 a second to about 200. 100-fold relief. And notice, we never touch the sharding rule at all. For read hotkeys, this is the first thing to reach for. So here is the ladder in one breath. Cheapest rung first, and each one for a different kind of heat. Salt the writes. When one key takes write fire, split it and spread it. Combine the increments. When the hot writes are counters, merge them at the edge. Isolate the whale. When one tenant is the heat, give it its own hardware. And copy the reads. When the heat is red traffic, a cache and replicas absorb it for you. The real skill here is diagnosis. Ask which kind of heat you have. Then take the cheapest rung that breaks it. One question remains, and interviewers love it. What happens when you add a shard? Here are 10 keys, living happily on 4 shards, routed by the naive rule. Hash the key, then take the remainder by the shard count. Now a 5th shard arrives, and the remainder changes for almost every key in the system. Watch this. 8 of our 10 keys stand up and move to a different home. That is roughly 4 out of every 5 keys. 80% of your data migrating under live traffic. Only these 2 get to stay where they were. That is not an expansion. That is removing your whole dataset while production watches. Hours of degraded everything. Consistent hashing is the fix, and it is delightfully physical. Place the servers on a ring. Each server owns the slice of key space that ends at its position. A key hashes to a point on the circle. Then it walks clockwise to the first server it meets. That server is its owner. Here is another key. Walking clockwise, same rule. And the rest of our keys settle in exactly the same way. Now the magic. Add a 5th server. It lands on the ring and it claims only the arc between itself and its neighbor. Exactly the keys on that slice rehome. This one. And this one. Everyone else never moves. 2 keys out of 10. 20% against the 80 we just watched. In practice, each server appears at many points around the ring. Virtual nodes, so the slices stay even. And failure runs the same movie backward. When a server dies, its slice simply flows on clockwise to its successor. One more growth shape is worth knowing, the fixed partition count. Up front, we create far more partitions than machines. 16 partitions say spread over our 4 servers. Every key hashes to a partition, and it stays in that partition for life. Now a fifth server joins, and nothing gets rehashed at all. Instead, we pick a few whole partitions and simply hand them over. Watch. 3 partitions slide across, keys and all, and the keys never even noticed. Each one still lives in the partition it always did. The partition just changed machines. Different mechanics, same goal as the ring. Adding a server moves a sliver, not the world. And all of it compresses into a few lines your router runs on every single request. At the top, a tiny set of the known hotkeys. Root takes a key. First, the escape hatch. Is this key on the hot list? If it is, we append a random salt 0 through 3 so the whale's heat spreads. Watch it run. The whale's key takes the salt branch. It lands on one shard this time, and a different shard the next. Otherwise, the normal path. Hash the key and ask the ring for the clockwise owner. An ordinary key rides that line around the ring to exactly one shard. A consistent hash for the crowd and an explicit escape hatch for the exceptions. Both halves of this lesson in code you can write from memory in an interview, so let's watch the whole idea one last time. A shard key is a rule that turns a key into a home, and the rule is the design. Pick it for your access pattern. When one key catches fire, climb the ladder. Salt the writes, combine the increments, isolate the whale, copy the reads, and grow on a ring. So that adding a server moves a sliver, not the world. Here is the phrase to leave with. Pick the key for the access pattern, and plan the whale's escape hatch before the whale arrives. Want to keep learning? Come find us at academy.rudewrite.com.